Hi folks, today we're going to kind of go over some work that I've been working on that allows you to use the OpenArm and spawn pretty much anything within the OpenArm's just its Cartesian range, or basically, and then pick that item up, sometimes successfully, sometimes failures. So here this is a success, but really is it if it's barely barely holding the cube? But I'm gonna go over what I did to make this happen. Let me move that out of the way. So you look here, the cube is being spawned on top of this box. I'm using a box because you know, I want the arm kind of rest a little bit above the ground. Oh, it kept it, but that wasn't really quite amazing how it. Let me just close that up too. Oh, opens again. And I'm actually just giving it a hard number of respawn 5 times just to make sure we're close enough. Yeah, you make a few adjustments to this. In this case, this is not the robot's issue, it's the depth camera that I'm using here. Need to make a few adjustments here so that so let's show you what the overhead camera is seeing. So this is what the overhead camera is seeing. It's a little high and away from the whole scene, so I have to bring the overhead camera down, and I knew that was an issue. And that's why the robot's having a little bit of trouble with the, you know, the full scene. So I'm gonna bring the camera down a little bit, but not very much, and get a little bit more of the scene. You want it to be as exact as possible. That way, when you start doing fine-tuning of models and training, etc., and training your policy, then the camera kind of represents where the rest of the robot actually is. Let's run it one more time, and I'm going to change to go to the right wrist camera so you can see what's happening there. So this is the right wrist camera. Starts off a little high, but the camera, right wrist camera, is actually where it's supposed to be. It looks like it hit the block and did not capture the, yeah, it hit the block instead of capturing the block, and that's because the overhead camera is off. Now that I just barely kind of got this whole thing working, and then obviously that's not good. You should not be able to hit the stand, but the stand is doesn't have a collision shape on purpose. I just didn't want to deal with a few problems at once. So now it picks it up, although I'm not excited about where it picked it up. I'd rather be more in the center. And this is something that you can tune, you know, small little things to get that right. But then I respawn again. It's kind of a weird view. Let's go back to perspective. And we'll get into this in a second, but I'm actually using that top camera and this other view to actually pick up the cube, and I'm going to lower this down a little bit before I start a training loop. But now that we've kind of gotten this part right, now let's get into you know, basically what all is going on. First of all, I'm using Gemini. Let's get to the top of this. This is the Gemini ER model that I'm using, ER 1.5. And I was really inspired because at the Humanoid Summit that just happened, I've been using this model for a bit of time since I got access, and I didn't quite understand what the impetus was, why we were. This model existed alongside another model I didn't have access to at the time, which is just the Gemini Robotics model. And I heard, you know, while there, that that model is going to be updated with Gemini 3, which is pretty awesome. I'm using Gemini 3 or Claude Opus now to do my model reasoning, and we're going to just briefly talk about what I use it for by using this context. You can see here, if I want to do something like, hey, label all of these points, the center of all of these things, I can do that. So here's some points. This is for the banana, the toy, the lime, etc. And it labels, those things, the bread slice. And, basically it just says, give me the object. And it's not saying center, it's just saying, give me the object and where it's at. And if you look, there's more things like this. I can say just, in this particular case, match the following objects: banana, starfruit, and bread. So it's not going to look at the rest of the scene. It's just going to give me those things, and and on and on and on. So here we have our, and this prompt says, find these objects and point to certain objects, right? So as the robot here is moving these items around, then the points are still being captured along, which is really important. This is basically object tracking. Here, bounding boxes, and all have examples. So, I can create images, bounding boxes, and all that other stuff that you can do. I get the semantic data. Here is the point tracking of the pen. And this is really important because, let's say I ran a robot whose job is to do, random cleaning of something, and I move the object around. Then I could still do that cleaning task. Okay, and then they kind of go over. Here's another one: point to the object and remove, make room for my laptop. So this has some spatial reasoning capability. So here are some things on the table. What do I need to remove? And then that actually is highly useful because there's some things like on board the robot, even with the Jetson Thor, I don't want to do. I don't want to reason across all these things and do object detection, etc. Now the Jetson Thor can do that, but saving it for all, I have running a lot of things in the Thor, a local processing unit, those kinds of things running on the Thor, where I'm taking certain models that I've running directly on the Thor when there's no internet. I still want to be able to do that. I don't want my robot to die just because there's no internet. But in this particular case, if I can say, if I have internet, use Gemini Robotics ER model, then do that. So we just kind of given an overview. This is kind of the flow that I'm using. I'm using this. In this case, is a mock API, but I'm doing the same thing. And actually, let me just show the code real quick. I know you guys like seeing code. Okay, so this is configuration file. I'll start with that, I guess. There's a default, this opening up this particular scene, which is the one you see in front of you, and then I have other ones. And as a matter of fact, I have a little bit of code that generates scenes where the gripper, the bimanual gripper, which we're using an OpenArm gripper, and the scene can be generated automatically. Now I'm actually working on a wheelbase for that gripper. That way the scene could be about anything, adjustable height wheelbase, and that way you can just say go to that position, adjust your height, and then pick up the object. Today it's just spawn a scene in which some item is within the Cartesian reach of the arm. So I have a bit of code that says, okay, figure out what the Cartesian reach of the arm is, and then from there, so test Cartesian control here, and that one will actually just go and say, okay, this is what I could possibly reach. So make sure the cube is within that position, and make sure that there's some thing that the cube is on, so that if we go back to our robot here, that as you can see, the arms don't extend to the ground. So it needs some kind of platform up above it, so that you can actually reach something below it. So let's run it again while I'm talking. That may give you a little bit more to look at other than my code. So you can see here it spawns at a random position. This stand, I did not make a collision body for that stand. It was unimportant at the time, but obviously when I go to train, it's much more important. And the thing that I'm not quite solid on 100% is when that camera is high up, like I have it, it seems to really struggle with then picking up the block. When I lowered the camera down, it was much better, but then didn't have a great understanding of the whole scene below it. So there's like a trade-off, and I think I'm going to lower the camera just a little bit, just so we can be absolutely sure what we're doing. The angle's right. That took a while to get the angle correct for the particular camera that I'm using, and you guys saw in a previous video. But here you go. It's able to pick up the block successfully and respawn, doing that 5 times, picking up the block. And then while this is running, let's look at the Gemini code running in the background. So I'm running what's called a Gemini coach, and I'm kind of playing around with what the coach is supposed to do. So first thing I'm going to say is I'm asking Gemini, plan waypoints for this particular action, and Gemini says, well, first lift the gripper vertically and avoid collision with the. Let's see if I can make this bigger. There we go. With the table, and descend to the grasping height, close the gripper, blah, blah, blah. So it's doing that, and I think we're still working on this little issue because it actually successfully reaches the waypoints. I think I need to make this a small range because it's not going to be ever exact. What I'm going to do is make that a tiny range, and that way this result will pass, even though it's showing failed here. It actually did, pick up the gripper again. It picked up the gripper again, and once I correct the camera view, it will pick up the gripper. I'm sorry, the cube much more reliably than it is now. Right now, we're getting about 80 to 90% accuracy. And that's fine for our application. This is supposed to be very, 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 capable of a dynamic environment, and you're not going to get 100% today in a dynamic environment, but you get really close. So, and the point for me is I'm super lazy. I don't want to build up a bunch of test data to run my tests. I'm going to just run this, and then this will give me enough test data. And so when we do that, transfer to the actual live robot, which I have code for as well, we'll do a little bit of calibration there, and then that'll just finish us off. Okay, back to the code. I know you guys are really always interested in code, so here we go. I'm running maybe a little bit more about this. So it's giving me 5 waypoints that I've asked for. Now I could have generatively asked for what I should do here. So what I can do is set up a basically task list. I could say to some model, give me, for what I'm trying to accomplish, give me 10 tasks, let's say, of what I'm trying to accomplish, or maybe not a number, but just look at the scene, use a reasoning model, and say what should be done here. Like for instance, if say I'm experimenting with plugging plugs into sockets, so I have a socket on my desk and I have a plug and a robot. So if I wanted to plug the socket in, this into the socket, what I want to do is say, hey, I need power. What are the steps for me to get power? And then, have that be reasoned upon, and then all the tasks that come out of it would just list itself here. Well, do I have a power cord? Yes. Okay. Is it a 2-prong, 3-prong, etc.? What kind of outlet do I need? And then as it goes through those, then when it comes up with physical tasks that it needs to do, then we go, iterate on those physical tasks. And right now I'm hard coding that. I was using that just to make sure that I can get my, kind of loop going the way I wanted to go before I go and start using this in training data. So what I'm doing is I'm recording the failures and the successes. It doesn't really matter from this, the camera positions, etc. And then I will go execute a record loop and train. But right now, the very first step for me was to make sure I can reliably respawn the cube and my camera's working and all that. This is stuff I've started like 2 months ago, 2.5 months ago, and I've been picking it up and putting it down because I have another complete robot that I'm working on. Okay, so back to a little bit of code. I think we talked about the config, but I'll start there again. This is what we're doing to create the environment, run server GUI. This is just my code that starts my Isaac Lab instance, and then what is that? Set cube position. That's right. Yeah. So I've just added in this maybe like a few days ago. So this puts the cube at a some place on the pedestal. I'm calling that box a pedestal. It basically looks at, okay, what's the pedestal size, and some random position on the pedestal size. That's right here. And then I ran some tests here. So first I tested Cartesian control, vision grasp. But first, before that, is I had to check, okay, for this robot, what are the places the robot can get to, basically. So this spits out all the Cartesian coordinates of that particular robot. And I've automated some of this. So when the robot's ingested from URDF file to USD file, I learn the IK like pretty much right away. And I have an API that runs that. And then from there, just spits out joint positions, and it does all of them, all of its possible states. And the reason why I'm doing that is because I don't want the robot to go in any unnatural state requested from Gemini. So now if we look at the Gemini client, you put your API key, and then to propose the plan, I'm using 1.5 Pro, but and then this is kind of hard coded, but that was only to just save a little bit of money in tokens, so I could use 2.5 or 3 flash models, save a little bit of money. And so here I'm hard coding the model ID, but this is something that's stanceable. I can change that to something else. And then I'm telling it about I have this robot, and this is what I want. I want to return, here's positions, left, right arm, right gripper, and the reasoning, and what we're calling the function name. So, I have these functions: move arms, move left arm, move right arm, set grippers, open gripper, close grippers, and then what I would do is just continuously add to this. If I wanted to say control the wheelbase or the height of the robot, I can add a new function here, right? Okay. And this is some information about, like, if I think of the prompt. This prompt is quite large, but I think it's right. It basically told it everything it needed to know about my robot before we got started. Here's some joint limits and some practical limits. I didn't see here, I'm not mentioning that there is that stand So if this is production, I would have to make sure that it knew about the stand, avoid the stand too, treat it as a collision, and that way it would never run into the stand. And then, we want absolute joint positions when we want to output those. And so this is kind of pedantic or type dict way of asking for my object back. So only give me this kind of object, don't give me anything else. And this model is really good at that. As a matter of fact, it'll error out on you or tell you you're asking for something different than what I'm supposed to give you, and it just keeps trying to tell you, hey, don't ask me for something that I'm not supposed to give you. So anyway, all this stuff is just loading the API keys and calling the model, stuff that we already know. Okay, so we talked about this, the joint range analyzer. It uses that learned IK, so it does this kind of look over the entirety of the positions possible, and then it learns IK from there, inverse kinematics, and create this as a service. So it spits out, I have a little dashboard that runs as well, and then all of the sessions get logged. So anytime we have any kind of experimentation, we're going to log all of those, the images that come out of it, the joint states, the time, etc. You can see here the time duration as well. And then the last thing I'll show before we get out of here is the vision grasp. We're going to test the vision grasp on the pedestal, and actually I'm going to run through a series of tests moving the camera to its natural position on the robotic arm. As we get into the hardware, there's a robot. It has a chest plate. On that I have cameras, and we want to take the camera view and use the exact position of the camera. That way, when we're sending that to Gemini, the cameras all line up. So I'm using, and actually that's an interesting thing to talk about. As you can see here, the camera could be adjustable all up and down this extrusion, so I can put the camera anywhere I want and kind of get the best view of my scene. There's a chest plate as well. I can just put the camera into the chest plate, etc. Same with the arm cameras, the wrist cameras. I've actually already hard-coded my camera here because that's the way I printed my my robot arm camera mounts. I just put it where I want, where it would not kind of interfere with anything else. So that camera is already positioned. This one is variable, so I can just say like, all right, I'm getting the best results from this particular spot or higher up, and just to close this out, I'll just run it one more time, since that's the fun part. People want to see robot move. So let's just go ahead and run it from here. I have a interface, so you guys might have seen from previous videos of many years ago. I like creating these little interfaces, actually, just so that you can talk to the robot, etc. And so you can see here, it's spawned here intentionally to try to make it more challenging for the gripper. And for the most part, except for the fact that the camera is a little too high, it's really good at grabbing this block. So what would I do in the next view? Obviously, I'm going to change this block to something else. Like, let's change it to something more temperamental with grasping. And now that we have all these assets from my friends at Lightwheel, we will randomize the asset. Yeah, it did not like that one. That was, I think it, and that's something where normally, yeah, nice job there. I'm happy that wasn't a medical supply that we needed desperately. What we would do normally is say, whoa, you missed. Like right now, I'm just going through a loop. But if you use a reasoning model on every step, then you don't yeah, it's a little slightly off. It's probably going to lift it, but yeah, barely. That's not amazing. Yeah. Oh, and I barely got it, but in reality it would slip out. But what I would do, and that's just a function of the fact that the camera's too high. What I would do is, in a normal environment, I would say, switch this out for something else, switch that out for something else, change the lighting conditions, change, we'll think of things to change, but really it's basically lighting conditions, objects, object stands, backgrounds, colors. Those are the things you want to change mainly. So I think this is a fairly long video, but I'm getting a lot of people asking me for the code. I don't post the code, because code assistance, you can go make your own code, read the docs, those kinds of things. You're not learning anything if you have me give you the code, especially when you can get the code from just pointing your favorite code assistant at the documentation. You can get all that yourself. Okay, but the main thing was to show off the power of Isaac Sim and the power of Gemini together. And if you look at it, that's quite awesome. The three things, or there's actually now three things involved here. I've got Groot, I've got Gemini, and I have Isaac Lab all running together with the OpenArm, which is an open source 7DoF arm with a gripper. In one of these videos, I know I've been promising this, but I will pull out the OpenArm and show you it running, or at least sitting there, and then we'll start after I've trained a bunch of episodes. We'll run the model on the OpenArm. Awesome. Talk to you later.